Hi everyone, my name is Kaizen and today I'm going to be talking through Step 2 1994, Question 5. Okay, let's get straight into it. So we have this equation here and we want to show that it has exactly two real roots if c is greater than 2, one root if c is equal to 2, and no roots if c is less than 2. Okay, interesting. So when you have questions like this with functions, when I first attempted this question, I immediately thought graph sketching and I thought turning points. Because if you can find the turning points of a function and you can look at the leading coefficient and think about how the function varies with x when x gets really, really negative or when x gets really, really positive, you can basically plot the function, or not plot, sketch the function, and you can see how that turning point affects where the roots are and if the roots are real or not. Okay, and you'll see what I mean as the video progresses. And that's going to kind of be our strategy throughout this entire question. It's going to be trying to sketch the function, and that's using turning points, and then trying to see, okay, how does that turning point and then what the function looks like relates to this changing value of c that we have here. Okay, so let's get straight into it, part I. Oh, on the rubber. Okay, so part I, I'm going to let f of x equal x minus 1 to the 4 plus x plus 1 to the 4. Right, now we can use our binomial expansion, our Pascal's triangle, to expand this out. So we're going to have our coefficients to be that. So f of x, equals, so we're going to have x to the 4. Now we need to be careful with that minus 1. It's going to be minus 4x to the 3 plus 6x squared minus 4x plus 1, and that's plus x to the 4 plus 4x to the 3 plus 6x squared plus 4x plus 1. That's just me expanding f of x. Okay, let's collect some like terms. This is going to be 2x to the 4. Now that cancels, plus 12x squared plus 2. Okay, so that's our f of x. Now we want to find the coordinates of any turning points of f of x, so we're going to differentiate and set the derivative equal to 0. So f prime of x is going to be 8x to the 3 plus 24x, and then that constant drops. So we're going to set f prime of x equal to 0 for turning points. Okay, so that's going to be 8x to the 3 equals minus 24x. That's me setting this equal to 0. Okay, so let's just divide through by 8 to start off with. So x to the 3 equals minus 3x. Now we see that x equals 0 is a solution. So x equals 0 is a solution. And by noting that on the side, that allows us to divide through by x. Okay, so now dividing through by x is allowed. And we can see that this equation here has no real values of x that satisfies that equation. That means that x equals 0 is the only turning point of our function f of x. So let's find f of 0. So remember, f of x was this thing up here. So f of 0 is simply going to be 2. So now we can think about what this function actually looks like. We have enough information to actually answer the first question. So we know the only turning point, and I learned this from R2 Drew 2, he's a fantastic YouTuber, you guys should check him out. Whenever I think of a turning point on a graph, I like to do a little straight line here that is parallel to the x-axis to denote a turning point. Now we know for our function, let me just write our function down here again, 4 plus 12x squared plus 2. We know our function is symmetric, and we know that as x gets very, 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 very positive, our function gets very, very, very large, and When x is very negative, our function gets very, very positive again. So remember, this part here is 2. Now we're going to introduce c. So so if we have f of x equals this, now we're going to consider, let's call this g of x. If c, right, if c is equal to 0, we have what we've drawn here. That c is equal to 0. Now, if c, oh, sorry, this should be minus c. Let me erase some things. And in fact, I'm going to call this f of x. And I'm going to put minus c. I keep forgetting this isn't another software that I use allows me to rub things out a bit easier. So remember, if we go back to the question, we have our function f of x minus c equals 0, which is what we have here. So what I'm graphing now, this is when c is equal to 0, because if we go back, right, I let f of x equal this thing here, and that's equal to c. So if I take away c, I'm going to have minus c, but when c is 0, I essentially just have the function that I've graphed. Okay, so now we're going to think about, what if c is equal to 2? Okay, well, if c is equal to 2, can you see how that's just going to be a shift of our entire graph downwards by 2 units? Okay, so our graph is going to look like this. That should pass through the origin. Okay, that's if c equals 2. Thus, when c equals 2, the graph of f of x is shifted downwards by 2 units. And there is exactly 1 real root, and that's at the origin. Okay? And we can say this is by a geometric argument. Okay? So, carrying on here, if c was less than 2, so for example, if c is 1, or if c is 0, or if c is, I don't know, minus 5, okay, can you see how there's going to be no real roots, right? C, and that was less than 2. Because, for example, if c was very, 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 very negative, because of this minus sign here, that actually means that the graph gets shifted upwards, right? That 2 negatives make a positive, so the graph gets shifted upwards. And then obviously we can say by the same argument that when c is less than 2, there'll be no real roots at all. Now, what about when c is greater than 2? So I'd write a similar sentence, but is that essentially what I said written down. So what if c is greater than 2? Well, if c is greater than 2, then the graph of f of x gets shifted downwards. Okay, so we have something like this for c greater than 2. And as we can see, that yields exactly 2 real roots. Okay, so that is the first part of our question. And I think if I was actually sitting the exam, I would have written out what I said. But because I'm just doing this spoken, you can kind of understand and then from that take it and just write it down as you need to. So let's move on to part 2. Alright, so with part 2, when I first attempted this question, I kind of did it how we did part 1. But like I've said in other step videos, part n always helps with part n plus 1. Well, not always, but most of the time for step. So we can actually make a substitution to make our lives easier. We're going to make the substitution u equals x minus 2. Because you know how we have x minus 3 to the 4 plus x minus 1 to the 4 equals c. When we let u equal x minus 2, that implies that x equals u plus 2. We have u plus 2 minus 3 to the 4 plus u plus 2 minus 1 to the 4 equals c. So then we have u 2 minus 3 minus 1 to the 4 plus u plus 1 to the 4. Now, that is the exact same thing as what we had in part I. So we can say by the same argument, the corresponding values of c will give the same number of corresponding real roots as this equation here. Okay, so the answer to part I is the exact same as the answer to part I. So let's move on to part triple I. So we've got this modulus function here. Okay, so we definitely want to start sketching this modulus function. Now, when we sketch modulus functions, I don't know about you, but I like to think about critical points. So when the inside here is equal to 0, when the modulus function starts changing sign. Okay, and for this function in particular, I'm going to split it up. I'm going to split up the plane into sort of 3 parts. I'm going to have when x equals 1, x equals 3. So when x is less than 1, when x is greater than 3, and when x is between 1 and 3. And we're going to investigate what's happening to, let's call our function f of x equals absolute value of x minus 3 plus absolute value x minus 1. Okay, so our critical points are going to be x equals 3, x equals 1, like we said. And now let's think about the 3 cases that we have. So let's think about case 1, when x is less than 1. So when x is less than 1, x minus 3, think about it. As x becomes more and more negative, this inside bracket here becomes more and more negative. So we're going to have negative x minus 3 is going to contribute a negative x minus 3 to our function f of x, because remember the absolute value function, right? It takes in x for x greater than or equal to 0, and takes in minus x for x less than 0. And because this inside here is going to be less than 0, we're going to take minus that inside bracket. Okay? Oh, apologies, I don't think you guys saw that. We're going to take minus that inside bracket. So, because we have x minus 3 here, okay, does that make sense? So we're going to take the negative of that inside, because for x less than 1, the inner bracket grows and becomes more and more negative, which means that, yeah, for x less than 1, the inner bracket's always negative. That means we take the minus of the inside bracket. Okay, I hope that's a clear explanation. Now we're going to do the same thing with x minus 1. The same thing happens with x minus 1, okay? When x is less than 1, that inner bracket is always negative. So we're going to have plus minus x minus 1. So this is going to give us minus x plus 3 minus x plus 1, which is going to give minus 2x plus 4. So for our function f of x, for x less than 1, we're going to have the equation 2x plus 4. Then we're going to consider the cases when x is between 1 and 3, and then when x is greater than 3. So let's consider 1 less than or equal to x less than or equal to 3. Remember our function here? Cool. So when x is between 1 and 3, let's think about x minus 3. Well, take for example x equals 0. You find that the inside bracket is negative. In fact, it's actually negative for all x between 1 and 3, except when it's 3 and we get 0. Okay, so that's always negative, so we're going to take the negative of the inside bracket. But x minus 1 within this range is always positive. So we're going to keep, oh, sorry, that should be a 1. Keep the sign of the inside. So we're going to have minus x plus 3 plus x minus 1. So that's going to give us 2. It's going to be constant. So if we go back up to here to our piecewise function, we have f of x is 2 for x between 1 and 3. Now let's think about when x is greater than 3. So for x greater than 3, again, we have our function here, x minus 1. We know this is always going to be positive for x greater than 3. And we know this is also going to be positive for x greater than 3. So we're going to have 2x minus 4. And now we can plot our function here. So it's going to kind of look like this. We're going to have 2 here. It's going to be 4. And it's going to go like that. Okay? And that's for c equals 0. Now remember, now we're going to consider minus c, some new function g of x. Really, this should be g of x, c. So, when c is equal to 2, what happens? Our graph gets shifted down by 2 units. So we're going to have something like this. And we see that for all x in this range, x is a root. Okay? So this is for c equals 2. For c less than 2, so when c gets very, 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 very negative, because of this minus sign, our graph gets shifted up. So, and that can be seen for our c equals 0 case. So c less than 2. So we're going to have no real roots, as you can clearly see by the graph. It's not going to intersect the x-axis for c less than 2. So for c less than 2, no real roots. Okay? And then the last case is for c greater than 2. Well, for c greater than 2, our graph is going to be shifted downwards. Okay, so we're going to have something like this. And we can clearly see that has 1, 2 real roots for c greater than 2. Exactly 2 real roots by our sketch. Okay, nice. So let's move on to the final part. We have x minus 3 to the 3 plus x minus 1 to the 3 equals c. Now, again, we can use that trick of the u equals x minus 2 to get x equals u plus 2 to get u minus 1 to the 3 plus u plus 1 to the 3 equals c. So now let's expand this out. We're going to have u to the 3. It's going to be minus 3u squared plus 3u minus 1 plus u to the 3 plus 3u squared plus 3u plus 1 equals c. Cancel, 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 cancel. So we're going to have 2u to the 3 plus 6u equals c. Now we're going to consider 2u to the 3 plus 6u minus c as our function. Okay, so our derivative is going to be 6u squared plus 6. Okay, and we start a derivative equal to 0 for a turning point. So we're going to have 6u squared plus 6 equals 0. 6u squared equals minus 6. So u squared equals minus 1. But again, there's no real values of u that satisfies this. So what does that mean? That means that the function has no turning points. So it's a cubic with no turning points. What does that mean for the roots? Well, that means there is always one root for all values of c. Okay, so it doesn't matter what c is. This cubic, there will always be a value of x for which y is 0, no matter what c is. Okay, but whoops, like terrible sketches of the cubic. But it will always cross the x-axis. Whoops, it will always cross the x-axis exactly once for all values of c. Okay, so with that last part, it doesn't actually matter what the value of c is, because this cubic has no turning points. There's always going to be one real root. Okay, so an interesting question there involving some interesting functions. We looked at real roots, we looked at derivatives. Hopefully you guys enjoyed this one. That's